Okay, well, it's a great honor and a pleasure to open this conference with so many friends here. I gave an intentionally vague title, but over the last few months to half a year, I've spent quite a bit of time thinking about the topic I'll talk about, and so I ended up kind of refining it to this. I'll like to talk about something which is, designed to understand thermal transport, although what I'll present is really more of a, let's say, a fundamental nature of trying to understand quantum kinetics generally for, including Berry phase effects for bosons. And there's a kind of subtitle here of Seeing the Stars. I thought this was not a bad image. You'll see it connects to the talk in some vague way. There's at least transport and kinetics going on in the background. So this is work really that has been done coming out of a, by now, pretty long collaboration with Lucille and her former student Leo, who's now a postdoc. And he'll be speaking later in this morning let's say, about more of the other aspects of this work and more ramifications. But this talk will be, somewhat more of a general nature. Okay. So there's a lot of interest in thermal Hall effect and in general thermal transport in quantum magnets. We'll see that throughout this program, and there are many motivations for it. But perhaps the most fundamental is that it's in some ways theoretically a unique probe of exotic phases. I think it was first pointed out by Alexei Kitaev as one appendix in his monumental work on the honeycomb model, that the thermal Hall conductivity in 2 dimensions in a topological phase, so a fully gapped, a highly entangled phase of quantum spins at low temperatures, is actually a universal quantity, and its coefficient determines a kind of fundamental property of the topological phase, something known as the chiral central charge. Well, we know now, after many years of study of thermal Hall effect, that thermal transport in quantum magnets is quite a bit richer than this simple topological physics, and we'll see quite a bit of it in various talks in this program. The next talk, I'm not sure, Leo's talk, Satoru's talk may have thermal transport in it. We had a couple more over the course of the week. We've already been discussing it pretty heavily in the program. Here are some images from a discussion, I guess, 2 weeks ago about thermal Hall effect and thermal transport in quantum magnets, and many issues were raised. Some of the questions that you might think about are what is actually carrying the heat? Is it in an insulator? Is it phonons? Is it magnons? Is it spinons? Is it something else? What is the origin? It's probably one of the most important questions of a Hall effect. Is it intrinsic? Does it come from some kind of Berry phase physics? Or is it due to scattering, interactions, impurities? Theoretically, we talked quite a bit about methods somewhere here. These are all sort of representing parts of this discussion. There's various theoretical methods that are employed. What I'll be talking about is kind of one of them. There are important issues in the theoretical calculations of separating transport versus bulk or magnetization currents. And there are many experimental challenges in these measurements that theorists also should be aware of. So I like to make a parallel with electrical anomalous Hall effect, which has been heavily studied and is, if anything, is simpler than thermal Hall effect, but nevertheless extremely rich and complex. This is an image from this, very well-known review article from Nagaosa and company, now more than a decade old, pointing out that there are many regimes. This is probably not enough regimes to really capture the richness even of the anomalous Hall effect. And you can see that there's a regime here, which in a way is kind of the most interesting one theoretically, where the physics is kind of simple and elegant, and the effect comes from this kind of intrinsic Berry phase of electron motion. But already in this picture, you see something kind of unexpected and strange. This intrinsic clean physics doesn't occur in the cleanest samples. The horizontal axis is conductivity. When they get clean enough, actually some other scattering mechanism dominates over this intrinsic regime. So, much as we might like to focus on the simple, elegant physics, it's clear we need a kind of complete description if we want to really hope to address these kind of complicated experiments. To my mind, the simplest, most complete description is a quantum kinetic equation, if only because it certainly can capture all this type of physics, and it's very simple. So this is just a version of a Boltzmann equation, and in general, this is what you might use to teach transport to a undergraduate class or graduate one. You have some distribution function that tells you how different modes of the system are occupied or not. It evolves according to some dynamics, which here is represented by some kind of convective derivative. And on the right-hand side, there's some collision terms. So all these intrinsic effects kind of fall into the left-hand side, and both extrinsic effects and interactions largely fall into the right-hand side. This collaboration that I've been spending time with Lucille and Leo over the past couple of years, initially we focused heavily on these collisions, and I think Leo will describe some of that work in his talk later. In this talk, I want to focus on this very simple thing, really just trying to understand how the Berry phase physics is incorporated into this type of description. So again, to put it in perspective, let's step back and see how this works for the electrical anomalous Hall effect. And it's extremely simple. It's so simple that you could teach it to undergrads. I haven't actually taught that course in a while, but I teach it to a grad class full of mostly experimentalists. And literally, you can capture the effect in 3 lines. You just write down that the current is the sum over all states of some density of states times the velocity of the electrons times the occupation probability. The velocity, and in particular the velocity contains the usual group velocity plus some anomalous term, which was actually derived back in the 1950s by Karplus and Luttinger, which is proportional to the electric field because it's the rate of change of momentum times the Berry curvature. So it enters in this simple way. This is the thing you need to explain is this, but once you understand it's there, which we understand very well now for electrons and solids, this immediately gives you an effect which is linear in the electric field. So this contribution, because it's already linear in the electric field, you can just use the unperturbed electron distribution, so replace F by the Fermi function, and you immediately get this formula. This is kind of simple and semi-classical, and yet in many respects it's exact. For example, if you consider filled bands at 0 temperature, you recover the integer quantum Hall effect. Okay. More complicated methods give the same answer. So we can ask about a similar intrinsic effect in bosonic systems. Okay, so in this context, we're interested in magnons and phonons, and back more than a decade ago, people started to think about the anomalous Hall effect, thermal Hall effect of magnons, and there's a well-known formula due to Murakami that basically relates this thermal Hall conductivity to the distribution function and the Berry curvature. It looks very similar. It's clearly kind of semi-classical in content. And there's, in fact, a similar formula for bosons, which the way it's usually written, for phonons, sorry, it looks a little different. But again, it involves just the Berry curvature and the occupation function. And in fact, even though they look a little different, I have to thank Jung Hoon for pointing out to us that, and Leo actually at the same time, that they're actually identical. So these formulas, they're completely identical. They're just written in a slightly different way. So where do they come from? You might think there'd be a simple derivation along exactly the same lines as I gave you, but in fact there isn't. The history is a little funny. This pioneering paper from Nagaosa, Patrick Lee, actually has a wrong answer. So that gives you an idea. These famous people made a mistake. There is some subtlety. Okay, it's more subtle than the electrical Hall effect. And this was fixed in the work by Murakami, and very soon thereafter by this paper, which is related to work by Chan Yu for phonons. But the calculations don't have the same level of simplicity and rigor. Murakami present a kind of semi-classical model, but it's very ad hoc, and it assumes the existence, for example, of a chemical potential for magnons. Since magnons don't really have a conserved number, it's a bit dubious. And the other calculations are based on quite surprisingly complicated calculations using a Kubo formula. Really this talk is about trying to do this using kinetic equation. Okay, and in particular, though, I don't want to just write down the kinetic equation, we want to derive it. So I'm going to present how this kinetic equation is derived, really without any approximations except the ones that are controlled in the limit of small temperature gradients. Okay. This is a kind of derivation of a quantum kinetic equation for bosons. Apart from the fact that the bosons are not interacting, there are really no assumptions. So I'm going to tell you that, but first I have to take a detour. I'm going to tell you about my sabbatical. I have a captive audience, you know, so I show you my vacation pictures. So I have to take you back a little over a year to the spring of 2022. I spent the first half of that year in France, and in the spring I was in Paris. I had this great office sharing with a bunch of famous people. I was pretty proud of this nameplate. Unfortunately, Nozier passed away while I was there, but still. We had rented this apartment on the Seine, which was pretty incredible. This is the view, you know, the first day from the window of my apartment. One of the benefits of Santa Barbara real estate prices is by renting your place here, you can actually afford this. Here's another picture at sunset from the same window. Okay, it was pretty sweet. So this is kind of an old Haussmannian-like building in Paris. This is a photo from the real estate place. The apartment was right here. You know, you go inside, it's quite, the courtyard and the entryway is quite sophisticated, let's say. In this place, it turned out the apartment itself was somewhat interesting. In the listing at the realtor, it was called Vicki Teal's apartment, and you could see her books, for example, on the bookshelves there. She was an intriguing character. She moved to Paris in the 1960s as a fashion model, and then became a clothing designer. This place was full of kind of wild stuff. It was a bit decaying. She really hadn't maintained the place. She was just renting it out. She lives in Florida now. Somehow I got on her newsletter. I get newsletters monthly about fashion. It's totally bizarre. But it was a beautiful place, but the maintenance was quite poor. I mean, like the dining table was literally falling apart. If you would touch the wrong part, little pieces would come down. And one day I ran into an elderly madame who lived in the building, who'd been there since probably the 50s. And sometimes these ladies like to talk, you know, anyone that age. I shouldn't say ladies, but in particular. And she was very chatty. She particularly, it seems she really didn't like Vicki. But she described her, she said that elle est très star, which I also really liked because it's kind of not, I guess, not real French, but, you know, someone who's very star. Kind of cool. And this has been incorporated into my language now. It turns out that being très star is actually the key to getting the quantum kinetic equation to work properly. Okay, so for the rest of this talk, we will attempt to be very star. And I should mention that I resisted being very star for a long time in this project, which delayed it tremendously, I have to say. I have to thank Leo and Lucille for dragging me reluctantly back into it. But to a large extent, we're sort of motivated by this work about a decade ago, which is deriving a quantum kinetic equation for fermions with all the Barry phase effects. Okay, so let me just kind of formulate the problem. So we have a set of Hermitian-Bose fields. Okay, we can always choose a Hermitian basis like momentum and position, things like this, or magnetization and a conjugate variable like staggered magnetization, and an antiferromagnet. And we assume we have a quadratic Hamiltonian. So in general, it doesn't need to be local, but it should be quasi-local. So we want some quadratic form in these fields, which should somehow be mostly support when the coordinates are near one another. And we, of course, need commutation relations. And again, those should be kind of quasi-local. And so there are, obvious constraints, like the Hamiltonian should be Hermitian. So this should be a Hermitian quadratic form. And this is antisymmetric and Hermitian. Okay, that's it. Okay, you can write them down for your favorite model. There's actually one more constraint which is important, which is that the Hamiltonian is bounded below in energy. Okay, turns out I won't explain where it arises, but it is important. And in general, observables, most observables, at least the ones we'll consider, the ones you need to know for transport, for example, are quadratic in these boson fields, and so we can define a quadratic form just in these two Bose fields. In general, we take a symmetric quadratic form. The antisymmetric part is trivial, it's just the commutator. And so this is some function of x1 and x2 and however many field components we have. So it's convenient to think about these quadratic forms as matrices. So you can multiply them both in the index and the coordinate space, and that's just like a convolution. So if we take two objects like this, two quadratic forms, we use this symbol convolution to indicate it's a convolution. We're multiplying in the coordinates and summing over the internal index. Okay. So with this notion, you can easily build the equation of motion for the field. It's just, according to quantum mechanics, the commutator of the field with the Hamiltonian. And we know the Hamiltonian in terms of little h, and then we know the commutators in terms of this matrix gamma, and it turns out it's just minus I gamma times h times phi. Okay. So this is some dynamical matrix. If you were writing, this is kind of the analog of the semiclassical dynamical equations for a bunch of spins, the block equations. K would be the dynamical matrix, IK would be the dynamical matrix there. Okay. And one thing you should notice, gamma and h are both Hermitian, but because they're multiplied in an order, k is not Hermitian. Okay. It's generally true if you just write the equations for position momentum in a linear system, that's not a Hermitian operator. So you can then do the same thing for this kind of density matrix F, and because it has two phis, the one on the left evolves and the one on the right evolves, and by the chain rule you just get k times F minus F times k star. Okay, so that in principle is the general dynamics for an object F, and now we would like to relate it to a semiclassical distribution. And that's done via the Wigner transformation. So you can take this F and transform, it's a partial Fourier transform. This is a standard basis of a semiclassical correspondence. Okay. So we need to Wigner transform this equation, and that means you need the Wigner transform of a convolution. We'd like to express that in terms of the Wigner transform of the two objects that are being convolved. Okay. So there's a very famous result, which is used heavily in the theory of semiclassics, which is that the Wigner transform of a convolution is what's called the Moiré product of the two Wigner transforms, sometimes called a star product. So Moiré is kind of an interesting guy, born in Jerusalem, lived in the US, in France, in Australia. He's one of the people responsible for developing this kind of phase space formulation of quantum mechanics. So this star or Moiré product, so here we're getting to be very star. It helps. This star represents a kind of exponential of derivatives, one acting on the first operator and one acting on the second operator. So this should be understood as kind of Taylor expanding this exponential order by order in some semiclassical parameter h bar. Okay. H bar is actually 1 everywhere in my notes, but you might want to think about this as an expansion in h bar. So this expansion is kind of good if these objects are slowly varying in position. Okay. So the h bar expansion is really kind of a slowly varying in position expansion. And this Moiré product has some nice properties. It's a lot like just multiplying operators. So the star product is distributive, and under Hermitian conjugation, you do just like a product of operators. You Hermitian conjugate the two Wigner functions. Okay, so this tells us that the Wigner transform of this kinetic equation is just a Moiré product, or this is something called, it's a sort of a Moiré bracket, where K is this dynamical matrix. So, in some sense, this is an exact kinetic equation, but it encodes a lot of stuff very compactly. You can ask, what would we like to do with it? Well, normally we have, these are kind of matrices, we should diagonalize it. Okay, so we want to diagonalize it, remove the matrix structure, and still we have to carry out a semiclassical expansion. That should give us the kind of semiclassical kinetic equation that we can use, and then we want to express physical quantities in terms of it. This Moiré product or star product allows you to do this diagonalization. I mentioned K is not Hermitian, so to diagonalize it, you need to use a similarity transformation rather than a unitary transformation, and there's some other condition that substitutes for unitarity. But these two conditions, equations define a kind of non-perturbative diagonalization of this dynamical matrix K into a new dynamical function. What you should keep in mind is this diagonalization is happening for every coordinate in phase space as a function of both K and X. Okay, so it looks like defining some eigenvalues, and Lucille thought we should call these stargenvalues. I think maybe that's too much, but if you do this, and then take F in the form, in a similar form, then this kinetic equation becomes diagonal. Okay, so conceptually, this equation is, it's in fact not that easy to solve because it involves this Moiré product, but you can do it order by order in H-bar very systematically. And at zeroth order, it becomes the usual diagonalization of a non-Hermitian matrix. Okay. So everything is kind of built on that. But the nice thing is this is a non-perturbative formulation that allows you to write the kinetic equation diagonally for just functions, not matrices, which are still functions in phase space. And then there's on top of this, there's a semiclassical expansion, which yields kind of a usual Boltzmann-like equation. So where does all the Berry phase stuff come in? So it comes in because there's some gauge freedom, as always in doing diagonalization. And in particular here, we can actually make a change of definition of this similarity transformation by some diagonal function lambda using the star product. And this keeps both keeps everything diagonal, the kinetic operator and the density matrix, but it does transform the frequency, the energy, and the distribution function. What's a little unconventional here is it really transforms both as a function of position and momentum. Okay, you're used to in the Berry phase theory of solids of transforming in K-space, but actually K-space and real space are mixed completely in this formalism. So it means that the thing that you might want to call the distribution function, this FA, is actually not gauge invariant, so it can't really be the physical distribution function. To make it physical, you need to introduce gauge fields. And those are kind of introduced as derivatives of the similarity transformation. Their diagonal part defines a U1 gauge field. And in particular, to define a gauge invariant energy and distribution function, actually the coordinates need to be shifted by these gauge fields. So these are kind of, this is like the transformation from canonical momentum to kinetic momentum for an electron in a magnetic field. So if you make this transformation, you can kind of convert this first order quantum kinetic equation to the form which is gauge invariant, and many things jump out at that point. In particular, you can see that these Berry curvatures appear, and one can recognize a lot of the kind of well-understood Berry curvature effects that we know and love from electrons already here for bosons. In particular, this is kind of an anomalous velocity term involving the Berry curvature in momentum space. There's also some Berry curvature in real space, and various mixed Berry curvatures that show up. Now, to talk about transport, we need to also, the third step of this program is understanding how physical quantities are represented in terms of the distribution function. So we'll be interested in the current. How do we get the current? Well, we get the current usually from the continuity equation. So we want, in this case, the energy current. So we wrote the Hamiltonian earlier. You can write this Hamiltonian as an integral over position and momentum using this Wigner representation. And in particular, you may remember that we defined the Hamiltonian as using this quadratic form h. It was multiplying quadratic function in phi, so it's something like trace of h times f, which is h star f, and to keep it Hermitian, one symmetrizes it. So this is a well-defined thing. We can now take the time derivative of it and use the equation of motion and check that it satisfies a continuity equation, which it does, it must. And in particular, you can read off the current here to first order in h bar. It's just something like this, and it should look kind of reasonable. This is some derivative of this k, which sort of substitutes as a dynamical matrix, so it looks a bit like velocity times energy times density. Okay. But at this point, these are Wigner functions, they're matrices, everything. So you need to express this in terms of these final distribution functions, you have to kind of undo things. So we introduced S to diagonalize K, we have to now invert it, write K in terms of this diagonal set of frequencies, and likewise for F. Okay, it sounds simple. This is where all the hard work comes in. Okay, there are lots and lots of algebra and a bunch of tricks. One can separate the current into two contributions. One contribution kind of looks like the usual kinetic contribution. You can recognize here something like a derivative of the energy, so a group velocity times a density. And the second contribution is actually a pure gradient in phase space, and there's some object here that I'm not going to even write down, but I use a symbol M because it looks like a magnetization. So this is what's called a magnetization current. It's has to do with sort of circulating currents. So in particular, if we unravel some of the complicated notation I use to make the formulas short, just write explicitly the electric heat current along a real space direction x. It is an integral over a quantity which involves the group velocity here, and a couple of anomalous velocity terms. The second term is really, as I said, a magnetization current, and it's a pure magnetization current. Because it's a derivative of something, if I actually integrate over the whole sample, this will always give 0. Okay. So in fact, the first term is all the transport current. Okay, so this is kind of a summary. These are basically all the general results, but we have formulas that now, if you have free bosons you can use, okay, and there's a procedure. You have to take your dynamical matrix and your commutation matrix and solve this equation order by order in h bar. Then you get a kinetic equation, which again needs to be solved, and then you can obtain other observables. Okay, in particular, you just directly obtain the transport currents. Okay, so this is kind of certainly not a short derivation, but in the end it could be used for lots of things. And just quickly, I'll mention sort of things that you could use it for. It has benefits. You immediately separate the transport current out. It enables you to calculate any local quantity you want. That's really the purpose of doing such a thing. You could calculate local current density or local temperature, or local energy density. And it's sort of ready-made to combine with other scattering effects, okay, which is really why we got into this. But just to maybe show you, to check that it works and to show you that it does simplify some things, once you've derived these equations, you can use it to quickly recover this formula for the thermal Hall effect. Okay, so here's a nice image I stole from Leo. Let's just consider a sample of finite width L with a temperature gradient along the y direction, and we want to calculate the heat current along the x direction. We want to get the transport current, so I'm only going to take this part, the transport part of the current density. The other part always integrates to 0 anyway. Because we have this local formulation, to get the conductivity, we really want the kind of leading term in the net current here will have a leading contribution, which is proportional to L. So we should integrate the total current and divide by L. Okay. And we'll divide by the temperature gradient, dyT. Now I gave you this formula here. J is the momentum integral of this current density in phase space. We'll consider a simple situation where our sample is basically uniform, except at the boundaries. In that case, we can drop these mixed phase space curvatures. The first term we shouldn't drop, but it gives 0 because it's a standard group velocity. It doesn't break time reversal symmetry typically. And we have this term, which is the anomalous velocity term. This is responsible for the effect. In particular, in this geometry, d omega dx is just d omega dy. And we want to take our distribution function here to be a function of the energy and of some local temperature that defines a temperature gradient. Okay, so that's just writing down that equation for the current. Again, as before, the equation is already, we expect that we can get this effect by just considering the equilibrium form of the distribution. So we just take, in that case, because this is defined as an energy, it's the frequency times the Bose occupation plus a half. That's the equilibrium form of this function. That's it. We want to stick that in here. We need to use a little bit of a trick. So there's a trick here is to define a sort of energy resolved conductivity if you want. This thing adds the contributions of the Berry curvature for every momentum state at energies below some epsilon. Okay. The reason to introduce this is if you take the derivative of this with respect to y, the only quantity here that depends on y is this energy, because something can happen at the boundary. You use a chain rule, you'll get a delta function times the y derivative of omega. So just using this form, you can actually write this equation as an integral over epsilon and y of dy of sigma times this form here. Okay. Now you integrate by parts on y. It lets y act here on the temperature. So that's the y derivative of this distribution. The constant gives 0. And now, because the Bose function is a function actually of energy divided by temperature, you can trade the y derivative, which is by the chain rule is derivative of temperature times the y derivative of temperature for a derivative of energy. So you can do a little algebra and convince yourself that this is equivalent to epsilon over t dy of t. In the large system limit, where this quantity is dominated by the bulk part, which is, so the integral is proportional to L, that L dependence cancels in the prefactor, and we just pull this stuff out, and you get the integral of this sigma of epsilon squared times the derivative of the Bose function. And that's actually the form in all these papers. Okay. So it's really just evaluating this formula. Okay. So that's it. Thanks for your time. Yeah, Leo will show you how to, I think in his talk, he'll show you a little more sophisticated application where you actually calculate the local currents.
So, thank you, Leon. So, questions from?
In earlier slide, as a background, you had this plot of, I guess, maybe it was for electric transport, where as a function of conductivity, and the extrinsic effects, the effects from scattering, set in at high conductivity. I would have thought it's the other way around. Maybe.
I told you it's surprising.
Yeah. Is there any thoughts? Can you explain is there some intuition for that?
Yeah, so those systems are always in the regime where the Hall conductivity is actually, even though that is actually very small compared to the longitudinal conductivity, so the Hall angle is small. So if you think, in that case, that means there are two types of scattering, okay? And we are interested in the limit where there's some, in general, it always exists. There's some, we call it skew scattering, could be side jump. There's several mechanisms of scattering that are, that actually break time reversal, that are chiral. They scatter, an electron scatters more to the left or to the right. That scattering rate is very small. But it adds kind of, I always forget this, adds in parallel to the kind of ordinary scattering, which is non-chiral. So one can kind of easily show that the net effect of that scattering actually is, it's proportional. You can kind of imagine it'll be proportional to the rate of the skew scattering. But you know that conductivities are proportional to scattering time, not rate. So just dimensionally, the conductivity is actually proportional to the skew scattering rate times the scattering time, the non-skew scattering time squared. Okay. So as the conductivity gets very big, this non-skew scattering time squared gets huge. And that sort of amplifies the effect of skew scattering. That's a simple-minded understanding, but it also comes out of kinetic equation.
Thanks for the talk. This mixed Berry curvature. So physically, when does it become important?
Yeah, it's a good question. I think it will become important, for example, if you have intrinsic spatial variations inside your sample. I think, for example, it might be important, I could imagine it'd be important in some systems with textures in the bulk.
Or some
okay,
disorder.
like skyrmions or something. Could be disorder, yeah. Yeah, so, yeah.
Okay.
Yeah.
Yes.
Thanks for the fun talk. I want to ask for the current associated with the magnetization, is it unique or is it gauge dependent? And you said if you integrate over the system is zero, but if you probe AC, can it become physical?
Yeah, I mean, one of the great questions is can you measure these local currents, period? So they're physical in the sense that these things are, they're defined, the current anyway, is defined by some Hermitian local operator that's gauge invariant. It's a totally fine thing in the original formulation. There's always a little bit of ambiguity in current operators. So there is some ambiguity. They're kind of defined up to some low order in wave vector terms. Given our definition of the current density, it's physical. It's completely gauge invariant, okay? But it's not unique in that sense. So I don't have a good answer how to measure it. I think it's something we're thinking about. I think there must be measurable in principle. What I think is more measurable, much more measurable, is a local temperature profile. That's a very measurable thing, and I know ways to do it even. But,
can I ask a second question?
Yeah.
So in the Moiré expansion, do you later keep the higher orders of H bar, or this is the order
you
one?
can. I mean, that's one of the benefits of it, is that in principle one can keep all the higher order terms. I should say that, in electrical transport, maybe here you can see it. I guess it was on that slide. Anyway, okay, the slide dropped out, but there we go. In electrical transport, one routinely actually keeps terms that are higher order than this, second order in gradients, okay? So there's a famous chiral anomaly, which is actually related to a higher order term. So I think that's certainly interesting to go beyond that, and the thing is completely set up to do it. We haven't done it at this point, but it would be interesting and possible.
Thank you.
Yeah, I'm just a naive experimentalist, so I have some very basic question. So could you say a little bit more about the relationship between semiclassical, Kubo formula, and this formalism? And I don't really understand the hierarchy of the, different treatments.
Oh, yeah.
And also what things cannot be done in Kubo or in semiclassical that you can do here?
So we use the word semiclassical. What does it rely on? It really relies on slow spatial variations. Okay, that's really the assumption. Okay, we build all the lattice scale physics into our into this matrix, these matrices. That's all the physics of magnons or phonons. Get those band structure completely correct. Then we say that the environment varies kind of on long scales. Okay, so that's an assumption, but it's, for example, when you apply a small temperature gradient, you're doing that. Okay, most of the time, linear response measurements at long wavelengths, the kind of things you do in transport, are entirely within the semiclassical regime. There's not really any approximation, and it shouldn't surprise you that it recovers the result of Kubo formula in that respect. But there, here we're doing semiclassics for non-interacting bosons. Okay, so interaction effects are certainly beyond this, but we know standard ways to add them to Boltzmann distribution, Boltzmann equation. Kind of physically, the important restriction of a Boltzmann or quantum kinetic equation is that you have quasi-particles. Okay, if you have some very strongly correlated system at a quantum critical point, you may or may not be able to apply a semiclassical description. Okay. But the advantage of quantum kinetic equation is you describe a non-equilibrium state. Okay, you can solve the Boltzmann equation not perturbatively around an equilibrium solution. As long as your non-equilibrium state varies slowly in space, you can find a solution. And so, what I like about Boltzmann equation, particularly for thermal transport, is you're actually including the physics of a non-equilibrium, that the temperature varies in space. The Kubo formula for thermal transport involves a kind of inspired guess of how that physics works based on Luttinger, some analogy with a gravitational field. The same thing for electrical transport is actually not a guess because there's a real electric field. For thermal transport, there's a kind of fictitious field analogous to the electric field that's introduced to do Kubo calculations. And depending on your inclination, that might keep you awake at night wondering if that's really kosher. But on the other hand, Kubo formula is great for interacting systems. Okay.
Christian?
Yes, thank you, Leon. So your expansion is an expansion in powers of H bar, so it's a semi-classical expansion. To leading order in H bar, this Moiré bracket becomes a Poisson bracket.
Right,
so,
right.
So in some sense, to the leading order, what you show by the end, you're doing the same thing that Murakami is doing, except for that you said that in their paper they have to introduce this chemical potential term by hand, and you are getting it somehow. I mean, you avoided that. So
yes.
Where is that? You avoid that. I mean, so how is it you can get that correction?
Because this formulation doesn't assume anything except that all parameters are allowed to vary slowly in space. That's it. Okay.
Because to leading order in H bar, seems like the two things are the same, right? So they are also working in phase space, when you do spin wave theory.
So what the thing about most semiclassical treatments is it's not actually derived, it's just written down. Okay, in the context of electrons, there is a sort of partial systematic derivation that is widely used, which is by Chun Yu, where he studies just the one particle problem using this wave packet formalism. Involves a bunch of leaps of faith, and then the step to writing Boltzmann equation is done entirely by hand. And just write down a Boltzmann equation with buried phase terms in it without deriving it ever. Okay, and you may wonder, particularly when you're kind of entering the semi-classical, not classical regime, if you're missing some physics. Okay, So that's really the difference. Is this is not, we just start with the full quantum dynamics at the kind of level of the density matrix, and work with it. But you're right. I mean, conceptually, there's not that much different in this final thing from what Murakami did. I think it's the first Murakami paper. There's a second Murakami paper, which is quite different. But yeah.
Hi, Leon. I was wondering if I could ask the question about the relationship with the electron systems. So let's say you wanted to do something similar for electrons. You write the standard kinetic equation, and let's say you have bosons present in your system, like electron-phonon scattering. So all of that would enter in a collision integral, right? You would have to write down exactly how your fermions scatter off of phonons. That's if you wanted to compute electric Hall effect. Now let's say you have magnons interacting with phonons, and you want to do the same thing. So what plays the role of the collision integral? So when I look at your equations, where is that interaction between bosons?
What we did basically had no collisions here, okay? This part had no collisions. We can add collisions. It's a separate calculation, really. But there's absolutely no problem in putting phonons and magnons together. I mean, I make no assumptions about what the bosons are. You just add more, make your matrix bigger. So there's another way to get a thermal Hall effect is actually when you have a mixing of phonon and magnon states. So that's been studied a few times in the literature where you form, I don't know, magnetophonons or some word for this, I'm sure.
That's right, yes. Right.
Electromagnons, thank you, good. Yeah, okay, where you've got admixtures of those. So that's
But if you had like density-density interactions, you would have to add that to the formalism you described, correct?
Yeah, that's right. Absolutely. Yeah. So, there is, I didn't talk about it, but of course in the electron context, there's a well-known formalism, usually done in Keldysh, to kind of correct the quantum kinetic equation using various interaction effects. They're both kind of Hartree-Fock type effects that enter on the left-hand side and their collision terms on the right. So, yeah. I didn't present it this way, but this is very close to Keldysh calculation. So I think one can do all these things.
Okay, so let's thank Leon for the nice talk.